Okay, so it's my great pleasure to introduce our speaker today, Professor Tejinder Singh, who will be talking about trace dynamics, octonions, and unification. Professor Singh obtained his PhD in physics back in 1989 from the Tata Institute for Fundamental Research in Mumbai, India, under the supervision of the late Professor Tanu Padmanabhan, himself a renowned general relativist and cosmologist. From here, he moved to ICTP Trieste, that's the International Center for Theoretical Physics, for a postdoctoral stay during the years 1989 and 1990. And then he returned to Tata Institute to join the staff there, beginning with a fellowship and then becoming successively a reader, an associate professor, and eventually a full professor at the Tata Institute, where he held a chair until the end of the year 2022. And beginning this year, 2023, he is a visiting professor at IUCAA. Those are the initials for the Inter-University Center for Astronomy and Astrophysics, where also the late professor, the late Padmanabhan, had a chair. Professor Singh's research interests are very wide, and they cover a very broad scope of fundamental issues in theoretical physics, in current theoretical physics. I'd like to mention four of them. He has done work on the foundations of quantum mechanics, also in cosmology, and more generally in gravity, both classical and quantum gravity. And more recently, he has become interested in the unification problem. So let me just say very briefly a few words on each one of these items. So in the topics concerning the foundations of quantum theory, he has dealt with the measurement problem in collaboration with the Trieste group around Angelo Bassi and Giancarlo Ghirardi and the Trieste group. So issues concerning wave function collapse, decoherence, and the problem of time. In cosmology, he has been concerned with the expansion of the universe, the cosmological constant, and problems about dark energy and dark matter. And more recently, he's also taken an interest in modified theories of gravity that go by the name of Mond and variants thereof, as developed by Mordechai Milgram. In gravity, either classical or quantum, he has worked on models of gravitational collapse, cosmic censorship, and also the problem of time. And as I said, in more recent years, he has developed his own approach to the problem of unification of gravity and the remaining three fundamental forces of nature. And he has succeeded in developing a framework which includes gravity and the three Young-Mills models for the other three models of nature, fundamental forces of nature, a model which is based on the symmetry E8 cross E8. Now, E8 cross E8 is not new in physics, of course, but the novelty in this approach is that it is based on considering the octonions as the fundamental numerical system to work with, as opposed to the usual complex numbers that are the rule. And one of the merits of this approach is that it provides a derivation of the standard model of particle physics, and in particular, of course, it includes gravity as well, but it also provides a theoretical derivation of quite a number of the 20 plus free parameters that the standard model has. So there is a rationale, a theoretical derivation for these parameters that have been experimentally measured, such as quark masses, CKM matrix parameters, Weinberg angle, and Yukawa couplings, and all that. So this is a very brief outline of his research interests. Over the last 35 years or so, Professor Singh has published some about 125 scientific research papers in highly prestigious journals. And I should say that many of these publications have received awards and distinctions. So, for example, reading his CV, I've come across 16 prizes and or honorable mentions granted by the Gravity Research Foundation Essay Contest. So that's basically almost every year over the last 20 years or so. And additionally to that, he has received 7 prizes and or honorable mentions by the Fundamental Questions Institute Essay Contest. Additional proof of the relevance of his work is provided by the fact that he has been funded by international agencies such as the John Templeton Foundation and the German Science Foundation. And these two in particular are notable for the generosity of their grants and by the difficulty getting them. So this is, of course, a further proof of quality. As an academic visitor, he has visited a number of many places around the world. I should mention here Southampton University in the UK, Cologne University in Germany, Trieste, where he was a postdoc at ICTP, and also the University of Trieste, which is a separate institution from ICTP in Italy. And he has also visited as an academic scholar, the Yukawa Institute for Theoretical Physics in Japan. And well, to finish this brief outline, I should mention that Professor Singh has carried out a remarkable amount of work in the popularization of science and in having increasing public outreach of science. He has written a large number of popular science articles that have been published in journals and given an even larger number of talks and seminars for a broad public, for a general audience. You will find them, many of them are available on YouTube. And he actually has his own channel on YouTube, which is literally loaded with goodies. You will find recordings of his popular science seminars, as well as more technical seminars for the specialist. I've watched and listened to many of them, and I have to say I've found all of them highly informative and highly enjoyable. So I would also invite you to take a look. Professor Singh is an excellent teacher. And if I may be allowed, just to finish this introduction, to make a personal assessment, I admire his deep physical insight and his rare ability of combining together many different inputs from apparently unrelated fields to produce a unified result that makes sense as a consistent whole. So in reading his papers, one comes across many different elements which are apparently unrelated, things like Adler's trace dynamics and the GRW mechanism for decoherence and Kahn's non-commutative geometry. And you would say, well, putting all these things together will give you kind of a pickle that doesn't make much sense. Well, no, it does make a lot of sense. And he has this rare ability of combining very different elements together to produce something which is strongly consistent and convincing. So I'm looking forward to this talk. Thank you.
Thank you, Jose. That was so kind of you to put things in perspective in so much detail. I try to do justice to the nice things and the kind things you have said today.
I'm sure you.
Thank you. So this is the title of the talk: Trace Dynamics, Octonions, and Unification, or we could also call it Gravitation and Quantum Theory as Emergent Phenomena. I should say this is a proposal for unification, but it is still work in progress. It is not complete, but we are hopeful that we have in place an outline which looks promising, which is what I would like to tell you about today. This work has been done in collaboration with a large number of young researchers for the last 4 years or so. I'm very grateful to them. Without their participation, this program would not have happened. So Maitresh Pelamkota, Abhinav Verma, Abhishek Pandey, MS Meghraj, Anmol Sahu, Abhinash Kumar Roy, Vatsalya Vaibhav, Rajrupa Mondal, Vivan Bhatt, Priyank Kaushik, Kartik Kakade, Aditya Kankur Patel, and Sherry Raj. And as was mentioned, we really truly stand on the shoulders of giants. So much work from other people has gone into building up this proposal. And again, I'm grateful to all of them and the subjects that they have developed, which we are now trying to use, like trace dynamics, the spectral action principle, of course, the octonions themselves, applications of octonions to the standard model, and the entire mathematical machinery of the exceptional Lie groups, and the theory of spontaneous localization, objective collapse models. I'm sure I missed out many important names. My apologies for that. Okay, so we would like to propose a path to unification. And here is the outline of the talk divided into 8 small sections. A motivation, new dynamics, namely trace dynamics, a new Lagrangian based on the Chomsky-Cohn's spectral action principle, a new coordinate system. Instead of R4, we will use the split bioctonions as coordinates. An old symmetry, as Jose said, this has been looked at before, E8 cross C8 and its branching. We bring gravity in a somewhat new way in this E8 cross C8 system. Clifford algebras, and they're used for understanding the particle content of E8 cross E8, the exceptional Jordan algebra, and attempt to derive some of the fundamental dimensionless constants of nature from here. And lastly, how to recover the observed universe from this framework. Okay, motivation. There ought to exist a reformulation of quantum field theory which does not depend on classical time. This is because the principle of quantum linear superposition does not permit the point structure of space-time, except in the approximation that the universe is dominated by classical bodies like today's universes. So if the universe was not dominantly classical, we are saying that the quantum linear superposition principle will destroy the point structure of space-time. It's a consequence of the Einstein whole argument. So we will lose classical time as a parameter, and yet we should be able to do quantum field theory. That is the goal, how to understand quantum theory without having to depend on a classical universe. And this requirement, the quantum theory without classical time, is clearly in principle true at all energy scales, not just at the Planck energy scale. Even in the low energy universe, if we remove quantum classical background, we need to redo quantum theory without classical time. Keeping that in mind, that energy scale is not what is important, we will use the following 3 fundamental units: one for length, Planck time, and action. LP, tau p is Planck time, and h bar. We have traded energy for action. Normally, we work with Planck length, Planck time, and Planck energy or Planck mass. We trade energy for action. So these are the quantities in terms of which other dimensionful of quantities should be expressed. If in a physical system, all subsystems have an action of the order h bar, the point structure of space-time is lost, because then everything is quantum. And according to the previous argument, we are now no longer having classical time if everything is quantum. In addition, and this, like I said, could happen at any energy scale. In addition to this situation, if all length and time scales are of the order Planck length or Planck time, then quantum gravity effects become important. And undoubtedly, quantum gravity becomes important at the Planck energy scale only. But quantum gravity becoming important and point structure of space-time being lost are 2 different things. You often conflate it with each other, but it should not be done. In principle, the point structure of spacetime does not exist even at low energies if all subsystems are quantum. In quantum field theory, loss of point structure is partly addressed by the Dirac operator, which can be thought of as a two-component quaternionic equation that is quite well known. So the Dirac operator, to a great extent, to a good extent, takes care of this issue for fermions, but time is still kept classical. We are working with a classical time parameter, but somehow we have smuggled in non-commutativity through the Dirac operator. So what we are in effect then going to do, extend the Dirac operator from the 4D quaternionic case to an octonionic space and employ Cohn's time, I'll describe that, for evolution. So we'll have a non-commutative space background from which we have to reconstruct space-time. And this will be octonionic, not 4D or quaternionic. And we are going to do this without change of energy scale. That's very important. Without changing the energy scale, we are asking what would happen if we work with the octonionic Dirac equation rather than the 4D Dirac equation. It will, of course, take us to higher dimensions, but those dimensions we will see effectively unify the vector bundle, the fiber bundle of gauge theories with our 4D space-time. So strictly speaking, we are not really introducing additional spatial dimensions by going to octonionic space, but we are unifying the vector bundle of gauge theories with our space-time. So a new dynamics. We heard about this from Steve in his very nice lecture a few weeks back. So I just try to bring back a few points from my perspective. The idea is very pretty. Suppose we were doing Newtonian dynamics or relativistic dynamics, not with real numbers, but with matrices. So this is, let's say, the Lagrangian, the action principle for a collection of point particles in Newtonian mechanics, or I can take the relativistic version. Let's replace these real numbers Qi by matrices shown here in bold. And the Lagrangian is now a trace of this matrix polynomial. I replaced M by LP squared by L squared. That's the parameter we'll be working with. Instead of masses, we have a length square or an area parameter. We take a trace of this matrix polynomial integrated over time. That is our new action. This is the essence of Adler's trace dynamics. And like he showed, we can derive equations of motion by varying with respect to the matrix Q using trace derivative. Now we'll have matrix valued Lagrange equations of motion, equivalently matrix valued Hamilton's equations of motion for the trace Hamiltonian. The phase space description can also be set. The very important new thing that comes in, which makes trace dynamics different from classical mechanics, is that there is a new conserved charge, which I like to call the Adler-Miller charge in honor of the authors who found it. You denote it as in Steve's talk by C tilde. So these matrices now in the theory will be made up of Grassmann elements or Grassmann numbers. They'll be of two kinds, QB and QF. They'll be called bosonic QB if the entries of the matrices are even grade Grassmann elements, and they'll be called QF if they are odd grade Grassmann elements. PB and PF are the corresponding canonical momenta. QB, PB is the commutator for this dynamical pair. QF, PF, the anti-commutator for the fermionic pair. Sum over all degrees of freedom. This is a conserved quantity as a consequence of global unitary invariance of the Hamiltonian or the trace Hamiltonian of the theory. So if these were real numbers, if Q and P were real numbers, trivially the conserved charge is trivially zero because Q and P commute. But here, this is a non-trivial charge. Notice that it has dimensions of action. In quantum theory, of course, we know in the Heisenberg algebra, each of these commutators is equal to IH bar. Here, that is not so. And yet the sum, each commutator evolves dynamically. Its evolution is determined by the dynamics. It evolves with the epoch, but yet this sum remains conserved as if all the degrees of freedom are exchanging action with each other. This defines pre-quantum theory. Even though we just went from real numbers to matrices, we go from classical Newtonian dynamics to a pre-quantum theory. This theory is more general than quantum theory, and from here, QFT is supposed to be recovered. So this charge makes all the difference. We are not just doing classical dynamics with matrices, we get much more out of it. Okay. From trace dynamics to quantum field theory, where the latter is an emergent phenomenon from the underlying dynamics, assume that trace dynamics holds at some time resolution tau p. Let's assume it is tau Planck time, or some time scale where QFT has not yet been verified. For, let's say, it is something about the electroweak scale. So some time scale above the electroweak scale, let us say trace dynamics holds there. It's a Lorentz invariant, matrix valued Lagrangian or Hamiltonian dynamics. And we ask this question, suppose we are not observing the dynamics at the resolution tau Planck, but at a lower resolution. So let's say not at 10 to the minus 30 seconds, but let's say at 10 to the minus 10 or 10 to the minus 15 seconds. What is the emergent dynamics if I coarse grain it over time scales? Let's ask this question first, assuming that the original Hamiltonian is self-adjoint. In general, the Hamiltonian of this theory is not restricted to be self-adjoint at the Planck scale. There's no motivation to do that. What Adler showed by applying the standard techniques of statistical thermodynamics, that the emergent coarse-grained dynamics is such that the Adler-Miller charge now gets equipartitioned. And once it is equipartitioned, being anti-self-adjoint, it is the same. It is imaginary, and it is now same for all degrees of freedom because of the equipartitioning. So we are allowed to set it equal to, since the sum is a constant because it is conserved, each of them are equal and constant, and we set that equal to IH bar, thus bringing in Planck's constant. These canonically averaged quantities obey the Heisenberg algebra in an emergent sense. And similarly, the thermal averages obey the Heisenberg equations of motion, and QFT emerges at statistical thermodynamical equilibrium from the underlying trace dynamics, which is more general than quantum theory. Okay, this is something I find very interesting. It's the side remark that trace dynamics admits what we call superquantum non-local correlations. So you probably are aware of the Popescu-Roerlich work on the CHSH inequality, which is a version of Bell's inequality, where a non-local correlation lies in the range 0 to 4. Classical systems, the one which, so to say, effectively have hidden variables, if that was true. And for classical systems, this correlation in this inequality lies between 0 and 2. Whereas relativistic causality would allow the correlation to go all the way up to 4, which is known as the Popescu-Roerlich bound. It's very interesting and surprising that quantum systems do not go all the way up to 4. Causality allows correlations as strong as 4, but quantum theory can only go up to 2 root 2, which is known as the Cyrillson bound. So these are quantum correlations. What we found, something we were anticipating, we tried to figure out for a year or two how to do a model. We found in a model that trace dynamics under those circumstances, when the Adler-Miller charge is not equipartition, will beat the Cyrillson bound and allow these super quantum correlations to arise. So it is as if the quantum correlations bound 2 root 2 is an attractor. If you go away from statistical equilibrium in the Adler sense, you can go towards classicality. But if the fluctuations in the Adler-Miller charges self-adjoin, you'd go in this direction and find these super quantum correlations. And when you go back to equilibrium, you'll come to 2 root 2 from both sides. I mean, classical systems eventually become black holes, which evaporate by Hawking radiation and become quantum again, and they will come to 2 root 2. But this is very interesting. If trace dynamics permits these non-local correlations, what kind of systems are there? We don't know how to make a system in a lab which will show such a super quantum correlation, which trace dynamics says ought to exist in nature. And if we find them, then that would be a very convincing proof that quantum mechanics is approximate, not exact. So that was a side remark, just a few additional remarks on trace dynamics. The underlying dynamics is deterministic. It is non-unitary, but norm-preserving. And if the anti-self-adjoint part of the Hamiltonian is significant, evolution breaks quantum linear superposition. And coarse-graining the dynamics introduces an apparent randomness in the evolution while obeying bond rules. So in this recent paper, we have tried to show the role of coarse-graining and non-unitarity is quite distinct. The underlying evolution is deterministic, but non-unitary and norm-preserving, which in principle, under suitable conditions, can break superposition while staying deterministic, and because of the non-unitarity. And randomness comes in only if we coarse-grain the dynamics, like we said in the Adler coarse-graining or time scales much larger than tau Planck. This maybe I can skip for now. Steve mentioned in his talk that there are two emergent sectors where this I effective matrix can be plus minus iota, where iota the complex imaginary. And only one of them is needed for quantum theory for the standard model. The other one could be the gravitational dark sector. And we do find that in the left-right symmetric extension of the standard model, which we are now going to see, there is a additional gravitational sector, which could be what Steve was suggesting. Okay, we have dynamics at hand, trace dynamics. Now we want to motivate how to include gravity in trace dynamics. So the trace dynamics considered by Adler has a flat space-time background, but clearly that is meant as a stopgap. Gravity is intended to be included. So now we want to make a proposal for how to use the Kohn-Shamsuddin spectral action principle to include gravitation in trace dynamics by considering a matrix-valued relativistic particle in quotes, which strictly will be a two-brane, it will be an extended object, but we don't start with a string or a two-brane. The equations of motions tell us that we cannot work with point particles if we want to make such a trace dynamics action. The equations of motions are inconsistent. We are compelled from first principles to have to work with a extended object like a two-brane. So taking clue from John Barrett's talk, has a much watered down version of the spectral action principle, which is basically I want to motivate what we are going to do. The Einstein-Hilbert action can be rewritten in terms of the eigenvalues of the Dirac operator. So in the Euclidean case, and we continue to assume that it holds in the Lorentzian case, if this is the Einstein-Hilbert action, it is equivalent to trace LP square D square, where D is the Dirac operator on the space-time manifold on which this gravity is being considered, up to order LP0 in the so-called heat kernel expansion of this trace, which can also be written as sum over the squared eigenvalues of the Dirac operator. Landy and Rovelli also showed that the eigenvalues of the Dirac operator serve as dynamical variables for general relativity equivalent to the metric. So, okay, so this is our starting point. Instead of the metric, we will use these lambda i's as classical variables, which we are going to raise to the status of operators or matrices. So the trace dynamics prescription of going to the more general dynamics will be applied to these eigenvalues of the Dirac operator. So here it goes. Every lambda, every eigenvalue of the Dirac operator is raised to an operator again. So now we have as many the operators as the eigenvalues, and which operator? The very Dirac operator of which it was an eigenvalue. So each such operator valued degree of freedom will be called an atom of space-time. A new configuration variable QB is introduced, whose time derivative is lambda I hat. So this is like a velocity. And the QB will be the configuration variable. The which time variable, because once we go to this eigenvalue space, we have lost space-time, but we know as a result from the so-called Tomita-Takisaki theorem applied to von Neumann algebras, and in particular to the Cohn's non-commutative geometry, that such non-commutative geometries, unlike Riemannian geometries, admit a one-parameter family of so-called inner automorphisms of the non-commutative algebra. And these one-parameter family of automorphisms can play the role of time. So that is very valuable for us. We have lost space-time because we have raised all these eigenvalues to the status of operators, but we have recovered Cohn's time. So the trace dynamics action for corresponding to each eigenvalue will be basically lambda I raised to an operator, which is QBI dot and QBI dot square, and then the trace, that the trace dynamics prescription. And in addition, this is new, integrated over Cohn's time. So this is something like it is already having a d4x integral hidden inside it, and then there's an additional fundamental time integral, which is not a part of the original space-time manifold. And we have to do this for each eigenvalue, and the total trace dynamics action will be sum of such actions, which we'll call atoms of space-time. And how to recover the classical space-time and gravitation back, the Girardi-Rimini-Weber process will be assumed to come into play when sufficient entanglement happens, and this operator will collapse to one of the eigenvalues, and all the eigenvalues together will then help us recover gravitation in the following. So spontaneous GRWP collapse is the opposite of trace quantization. Trace quantization consists of making these eigenvalues into operators, and then there's a reverse process. Okay, so this part is so far only bosonic. It is in concerning only gravity. We want to bring in fermions, and this is the proposed Lagrangian. Let's have a look. There was QB dot square. I've replaced that by QB dot dagger and QB dot and added a fermionic part. This QF is a fermionic matrix. And now beta 1 and beta 2 are two constant Grassmann elements introduced to make the overall Lagrangian and hence the action bosonic. We don't want the action to be fermionic. The Cohn's time is scaled by tau Planck. This is a fundamental area or length parameter which characterizes this space-time matter. In fact, this is the only thing which will be there. It's an area parameter. And this is what I call a two-brain because it's like there are now two-dimensional degrees of freedom because beta 1 and beta 2 are non-equal. And why did we introduce beta 1 and beta 2? We found that if we don't do that, we don't get consistent equations of motion. The only way we could find to have equations of motion for these bosonic and fermionic variables was to by hand introduce these unequal Grassmann elements, beta 1 and beta 2. For future reference, all dotted variables will relate to gravity. Dotted fermionic variables will be shown to be right chiral fermions. QB dotted bosonic variables will have to do with the gravitation. How do we include Young-Mills fields? I should mention there's a spectral action principle once the Young-Mills field vector potential is also included. Basically, D goes to D plus EA, where E is the Young-Mills coupling, A is the Young-Mills vector potential. And when you expand with the heat kernel expansion, along with this, we will get the gauge field Lagrangian for Young-Mills fields and some gravitational corrections, not to worry about that right now. So our proposal to include Young-Mills in addition to gravity is to treat that as a configuration variable corresponding to this momentum QB dot. So every QB dot you see here has been, I add Young-Mills coupling constant alpha and Young-Mills configuration variable QB. Similarly here, this will become left-handed fermions of the standard model. The dotted fermions will be right-handed fermions. And similarly, there is a inclusion of Young-Mills in these terms. So you can map. This object is what we call an atom of space-time matter or an icon. The universe is made up of very, very large, maybe infinite of a very large number of copies of these atoms of space-time matter. For our talk, most of the talk will be concerned with just one. Also, I call it an icon. We just concerned with just one icon, which will be described by this full action. We'll introduce the coordinate system now shortly. Equations of motion can be found by redefining these variables Q1 and Q2 like this. The equations of motion are quite simple. They are discussed here. And we can also write the action in a very simple way by defining this capital Q bosonic variable, which adds the gravity and the Young-Mills part. Similarly, it adds the left and right-handed fermions. Then you can add the bosonic and the fermionic part for the beta 1 case, for the beta 2 case. And in the end, the action looks very simple. In classical mechanics, this is known as the Bateman oscillator, two coupled oscillators, one of which is inverted harmonic oscillator with equal and opposite energies. So this is what we could also call a two-brain, one elementary particle, which includes both the bosonic and the fermionic aspects together. And this is the form prior to left-right symmetry breaking. Each of these objects is now going to be defined over a 16-dimensional coordinate space, and this Lagrangian will be assumed by hand to obey E8 cross E8 symmetry. Okay, so we have the dynamics, trace dynamics. We have the Lagrangian, which I just showed you, motivated by the spectral action principle. Now we want a coordinate system on which to write down these dynamical variables. And the motivation is that we don't want to work with R4. In quantum theory, we cannot have a commutative space-time manifold for reasons discussed right in the beginning. And for various reasons, it turns out that what we are going to do for each degree of, so like I said, the universe is consisting of, let's say, infinitely many copies of this action. This is one elementary particle, or ion is a fermion along with all the bosonic fields it produces. So electron, along with this electromagnetic field, along with the weak interaction, along with gravitation, all that put, so it's like we don't distinguish between a particle and the bosonic fields it produces. All put together, that's one entity, which is called atom of space-time matter. And that is the action for this. As you can see, the bosonic and fermionic parts have gone in together. And that atom of space-time matter, or the ion, is going to live on an octonionic space, one copy of the octonionic space for every space-time matter atom. So every particle, every STM atom has its own coordinate system. This is very important to remember. In the end, we are trying to recover space-time from localizations in this multi-dimensional space where every particle has its own coordinate system. The algebra automorphisms of the octonionic space unify gauge field transformations and diff space-time diffeomorphisms without any change in energy scale. So we want a unified description of the vector bundle and the space-time manifold. This is familiar to us that there are only four different kinds of norm division algebras, the quaternions, and to some degree, at least one can think of the Dirac operator as the gradient operator on the quaternionic space where I hat, J hat, K. So at least the Laplacian is easy to see. The Laplacian is the square of the gradient on the imaginary quaternionic space. So keeping that spirit in mind, our action, if I may go back once again, is nothing but effectively the Dirac operator squared, or a bilinear in the Dirac operator, like kinetic energy. This is really the kinetic energy of a free particle at the matrix valued level. Okay, and we know that the various division algebras relate to Lorentz groups in 4, 6, and 10 dimensions, making 4, 6, and 10 special, 2 more than the dimension of the division algebra. So SL2C is a double cover of SO13 and so on. So what is the idea? The bosonic and fermionic degrees of freedom live on octonionic space, more precisely on the split bioctonionic space. I'll come to that in a moment. So what does that mean? If this is my coordinate system, 8-dimensional coordinate system, the bosonic variable has 8 matrix valued. So this is like we do for a vector. Now we are doing it for a matrix. Each of Q0, Q1, Q2 are matrices. They are bosonic matrices, and I can do the corresponding thing for the fermionic matrix QF, which will have 8 fermionic matrix valued components over an octonionic space. And we make this a little more specific now. Okay, so we actually want to define our bosonic and fermionic matrices over, not over a 8D space, but over a 16D space defined by split bioctonions, because that allows us to have chiral fermions and standard model gauge fields as well as gravity. So what is a split bioctonion? A split complex number omega is defined such that omega square is 1, but omega is neither plus minus 1, and yet there's a conjugation, omega star is minus omega. So this is a split complex number, which is written like z equals a plus omega b. And this is what we might call a split bicomplex number. So the preceding split biquaternion is a split bicomplex x plus iy plus omega x minus iy, where I is the usual imaginary square root of minus 1. Okay. What is a split biquaternion? Recall that the algebra CL01, Clifford algebra CL01 is complex numbers. CL02 is quaternions, 1, E1, E2, E1, E2. This is the quaternion. CL03 will have 8 elements. 1, E1, E2, E3, E1, E2, E2, E3, E1, E3, and E1, E2, E3, the pseudo-scalar volume element, the scalar 3 vectors and 3 bivectors. We can write this as a pair of quaternions. The second one's also a quaternion. And in the second one, we can pull out an omega. This is what is left inside, where omega is the pseudo-scalar volume, 1, E1, E2, E3. And now we can see that CL03 is the algebra H plus omega H. And this is the definition of a split biquaternion. A split because omega actually now behaves like the split complex number. Omega square will be 1. It has just the same properties as the split complex number. That's why this is called a split biquaternion, which we can also write as C prime cross H, where C prime is the split complex number. So this is the algebra CL03, which generates the split biquaternions. And what is good for us is parity reversal, that the second one is the parity reverse of the first one. So if we use one of them to define left-handed fermions, the other one will be used to define right-handed fermions. So CL03, when complexified, so okay, how to complexify? CL2 is the complexification of CL02, C cross H. Complex split biquaternions are complexifications of CL03, which is C cross H plus omega H, which is essentially 2 copies of CL2, which will permit us to define the chiral leptons. And similarly, if we want to go to include quarks, we'll have to go to CL7, which will be 2 copies of CL6, as we'll just see. This is new and interesting. Consider now, I want to multiply the split biquaternion with its conjugate. So H conjugate, this is the quaternionic conjugate. Omega goes to minus omega, which is I'm trying to indicate that by the symbol, and H tilde. See, H tilde, because this is parity reversed. So I call this H tilde, and multiply it by its quaternionic conjugate, H tilde minus omega H. And let's open it out. Something very interesting happens, and which is essentially the following. I mean, I'm multiplying this object by its conjugation, quaternionic conjugation, and this is the result. We get 2 Euclidean spaces. These will not cancel with each other because they are actually coming multiplied with dynamical variables, trace dynamical variables, which don't commute. So there are no cancellations here. See what's happening. If we work with the split biquaternion and essentially square it, we get 2 Euclidean spaces and 2 copies of 4D spacetime with imaginary corrections under circumstances where imaginary corrections are ignorable. This becomes 2 copies of Lorentzian 4D spacetimes and 2 Euclidean spaces. This is what I call the unification of the vector bundle and the spacetime. They are both present in the squared split biquaternion. and similarly in the split bioctonion. So it looks like the biquaternions and bioctonions are very significant in the process of unification. They allow us chiral fermions because of this parity symmetry, and they allow us, in a sense, the unification of the fiber bundles of gauge fields with space-time. Both are present in this split bioctonionic structure. So this is H plus omega H is like the square root of space-time plus vector bundle put together. So it's as if we are now doing a Kaluza-Klein theory at the quaternionic and octonionic square root level. We don't introduce the metric or the Kaluza-Klein higher dimensional metric at the level of space-time or Euclidean space. We introduce trace dynamical variables which are equivalent of the Dirac operator at the level of the biquaternions or bioctonions. And then when we will square, keeping in mind the spectral action principle, we expect to recover gravity and the standard model gauge fields. But at this level, we are already going to see unification at the quaternion, the biquaternion level. So similarly, we can now define split bioctonions. The complex octonions are generated by the Clifford algebra CL6, which is the complexification of CL06, giving C cross O. Complex split bioctonions are the complexification of CL07, and as you anticipate, it is C cross O plus omega O, where omega is now the split complex number made from these octonionic imaginaries. And we know that we have to work with octonionic chains if we want to generate a Clifford algebra, because octonion multiplication is not associative. This algebra, CL6 plus CL6, will give us chiral quarks and leptons, one CL6 for left-handed ones, and another CL6 for right-handed ones. Once again, when we square O plus omega O tilde, where now this is an octonionic conjugation, you open it out, you see a higher dimensional Euclidean space and a higher dimensional space-time emerging, suggests that the 16D space defined by the split bioctonion unifies the space-time manifold with the vector bundle. Of course, this is higher dimensional. It turns out we need this if we want to have quarks. If we only want leptons, we could do with the split biquaternions. The Lagrangian of the theory, which I showed you earlier, is defined on this 16D space and will be assumed to have a E8 cross E8 symmetry. So what is the 16 doing? QB dot plus QB will be 16 dimensional. I think I showed that. I'll show that later maybe. QB dot plus QB will be 16 dimensional. The dotted variables will be defined over the second part of the split bioctonion, that will be right-handed and gravity. The undotted variables will be defined over O. So 8 components for QB, 8 components for QB dot, 8 components for QF, 8 for QF dot, and this is the second part of the Lagrange. So I have tried to introduce a coordinate system on which the trace dynamics action is playing out. And what is the use of this coordinate system? It goes well with the E8 cross E8 symmetry, which we would now like to introduce. Okay, so this was proposed by Priyanka Kaushik, Vatsalya Weber, and myself last year. E8 cross E8 unification of the standard model and pre-gravitation. This is what emerges after the proposed branching. 6 forces instead of 4, SU3 color for QCD, SU2L, cross U1Y for electroweak. This is what comes from the branching of the first E8. From the branching of the second E8, SU3 grav, this is new. SU2R, which we expect will become general relativity, and a U1 correction corresponding to U1Y, which we are investigating if it is the relativistic theory of Milgrom's Mond. So this E8 cross E8, I'll now show, is defined on a split bioctonionic space. It is known that E8 has a branching SU3 cross E6. So 248 dimensions. So this branching, we break it into two separate E8s like 248, 1, some 1, 248. Each E8 branches into a SU3 cross E6. The first one is assumed to branch as a SU3 space 1 cross E6. By space 1, I now mean the O part of the split bioctonion, and by space 2 will be the omega O part. So what we are imagining, this SU3 can be mapped to the 8D vector space, which in turn is related to the octonionic space. So this is the coordinate system. The coordinate system itself emerges after the branching of E8, and E6 will be for matter fields, fermions, and gauge fields. The second E8 branches into SU3 space 2 crosses. By space 2, I now mean the omega O part of the split biocton. So between themselves, SU3 space 1 cross SU3 space 2 together define the 16D split bioctonics on bioctonionic space. So these two SU3s for the space background on which the fermionic and gauge degrees of freedom, including gravity, will live. This is a well-known branching of E6, known as trinification, which has been looked at by others, but we do something different with it now. The 248 of E8 can branches like this: 8, 1, 178, 327, 3 bar, 27 bar. All these 378, 27, and 27 bar representations of E6 make their appearance. For the first E6, the left-handed one, the interpretation is SU3, one SU3 for 3 generations of left-handed fermions, one SU3 for color out of these, and the third SU3 can be further branches as SU2L cross U1Y. It gives the left-handed fermions of the standard model, or I'll come back to it again, along with the standard model gauge fields. So important to remember that for E8, the fundamental representation is the adjoint representation, which is good for us because prior to symmetry breaking, we are not making a distinction between bosonic and fermionic degrees of freedom. The second E6 is given the following interpretation after trinification: 3 generations of right-handed fermions, a new force, SU3 grav, whose properties we need to understand. And the last SU3 branches as SU2R cross new U1 symmetry, which is different from the weak hypercharge and from electromagnetism. This is what we call pre-gravitation. As you know from Colfury's talk, the U1Y is related to U1 electromagnetism. She showed charge quantization. But for us, this U1 here will not be electric charge. It will be a new quantum number, square root of mass. It's a newly introduced quantum number. So electric charge and square root mass are both emergent after this branching. And it can be shown that the Lagrangian possesses this gauge gravity duality. You can exchange dotted and undotted variables, and the Lagrangian will remain invariant. Okay. So what is the particle content after branching, total 496 degrees of freedom. The left chiral part, the first E6. Uh, this is the standard model, doublet, up quark, and down quark. These are generation triplets, so 3 generations. They are color triplets. They are weak doublets. This follows from the branching shown in the paper with hypercharge 1/6, giving the expected electric charges for U and D. And if you include antiparticles, there are 36 left-handed quarks. Similarly, the electron neutrino and the electron are generation triplets, color singlets, weak doublets. And if you add them all up, you get 12 left-handed leptons. And the adjoint representation shows there are 8 gluons, 4 electroweak bosons, 4 Higgs. This is, by interestingly, not the standard model Higgs. It's a new Higgs, that we have 2 Higgs doublets in this theory, one electrically charged and one massive. So that's this total of 16 bosons. Interestingly, when the branching, because our E6 is coming from the branching of E8, some of these states are space 1 triplets. They are triplets of this space 1. And okay, so this is the branching of the first E8, and the quarks are space 1 singlets, leptons are space 1 triplets. So 12 into 3, 36. 36 plus 36, 72 left-handed fermions, 16 bosons, 8 for degrees of freedom for space 1, 8 for the internal space for 3 generations, and the total gives me 104 degrees of freedom. We repeat this for the second E6, but now with a different interpretation. SU3 gen for 3 right-handed generations, SU3 grav, and I'm branching into SU2R cross U1 gamma 2, which is related to U1 grav. Now the U1 grav charge is square root of mass. So what is going on here? From experiment, we know that whereas the down quark's electric charge is 1/3 that of the electron, the down quark's mass is 9 times that of the electron. So the square root of the down quark's mass is 3 times that of the electron, whereas the up quark is 4 times massive than the electron, and its square root mass is twice. So the electric charge ratios for the down, up, and electron are 1, 2, 3, but the square root mass ratios are 3 to 1. We find this very significant and not a coincidence. So U1 grav charge is defined as square root mass. Notice here, it still has value 0, 1/3, 2/3, 1, like for electric charge, but we have interchanged the position of the electron and the down quark. If the electron has a root mass of 1/3, the down quark has a root mass of 1, and the up quark remains unmoved, and this is now the right-handed neutrino. For each of the 3 generations, the square root mass will have the value 0, 1/3, 2/3, 1. Now, however, we know that the second and third mass ratios of generation mass ratios are very weird for the second and third generation. The muon does not have the same square root mass as the electron. It is 200 times heavier. So why do we see those strange mass ratios, whereas fundamentally we are proposing this? So we see that in a moment, where the weird mass ratios come from. So keeping this in mind, we now have a SU3 grav triplet made up of the up quark and the electron. The up quark and electron, right-handed up quark and electron, are generation triplets, gravicolor triplets, pre-grav doublets with pre-grav charge 1/6. And so we can go through the same process, but now notice the neutrino is associated with the down quark in a doublet. nu D and R, these are generation triplets, nu D and the down quark right-handed, but they're gravicolor singlets, SU3 grav singlet. So the down quark is a SU3 grav singlet, although it is a SU3 color triplet. And these are the masses, 0 for the down neutrino, and -1 for the down quark, consistent with this proposal. Again, once again, we can do the counting. And in the end, we get, once we take account of these space triplets, once again, we get 36 right-handed quarks, 36 right-handed leptons. And if you add all this, 72 right-handed fermions. So what are the right-hand? These are new particles. SU3 grav cross SU2R cross U1 grav gives us 12 new bosons, 8 gravigluons, 4 dark pre-grav bosons, 4 additional Higgs degrees. This is the standard model Higgs. The standard model Higgs is coming from the right-handed sector. Once again, a total of 16 bosons. If you add all this up, we get 208 degrees of freedom. And so what about the remaining 496 minus 248? From the Lagrangian and for various other reasons, we would like to suggest that there are no more new particles apart from what I've already mentioned. And the two Higgs are in fact not scalars, fundamental scalars. They are composites of left-handed and right-handed fermions, each having 144 degrees of freedom. Notice this 72 right-handed fermions plus 72 left-handed is 144. And what is left is 288. 208 is explained. 288 out of 496 needs to be accounted for. And we propose that those go into forming two composite Higgs, subject, of course, to future experimental confirmation. So the total is 32 for bosons, 32 for space 1, space 2, and generation internal space, 144 for the fermions, standard model fermions, 144 for one Higgs, 144 for the other one. This is our proposal, that this is how the E8 cross E8 is saturated without having to anticipate some new heavy particles at higher degrees of freedom. Matter and antimatter have opposite signs of root m. See, mass is positive, but root, when we take the square root, it comes with two signs, minus root m and plus root m. And we can argue that in the very early universe, these are segregated from each other, so that our universe only has matter, which is minus root m, but the square gives us positive mass. Okay. So, Jose, how are we doing on time?
Well, you've been speaking for 60 minutes. I would grant you another, say, 20 minutes or so, or 30, if...
Okay, so 20 to max 30, we aim for 20.
Is that fine? Yeah.
That should be good. That should be good, yeah. So
Okay.
we have the Lagrangian, we have the trace dynamics, we have the coordinate system split by octonions. So let's recall once again that the E8 cross E8, one E8 gives me degrees of freedom, which is defined on the first 8D part of the split by octonion. The other E8 gives me degrees of freedom, which are defined on the second part of the split by octonion. And so that gives us chiral fermions, standard model gauge bosons, 16 new gauge bosonic degrees of freedom. And that's about it. So we think we probably know, at least as a proposal, the full story for what we want to do with this branching of E8 cross E8. Okay, so we analyzed the Lagrangian after expanding it over this split by octonion expression. So this you have seen. So this is a 16D object as shown here. And the split by octonion is this quantity. So we expanded, uh, so this is the bosonic part of the Lagrangian we have worked with so far. We open everything out. We want to know if the symmetries that are seen in the E8 cross E8 branching are seen in the Lagrangian. And at least we are happy that for the bosonic part, we have worked everything out in detail. And we confirmed by constructing generators for SU3 and SU2 that the Lagrangian that I showed you does exhibit the E8 cross E8 branching that we claimed. So there are when you open all these terms out, there are 8 gravigluons and a dark photon consistent with this symmetry. There is 8 standard model gluons and the photon are also present. 3 weak bosons, 3 pre-grav bosons. These are new. So these 9 and 312, and there is evidence for the presence of 2 Higgs in these terms, which are real valued. The B0 component QB the 0 dot Q dot square B0 and Q square B0, these are real quantities. And along with certain components coming from the fermionic part of the Lagrangian, it seems that we have 2 Higgs and the desired bosons. We are yet to fully analyze the fermionic part and convince ourselves that that has 3 fermion generation. That remains to be done. But by looking at the bosonic part of the Lagrangian, we could compute the low energy weak mixing angle, which satisfies this equation, and it gave us a result which is not in great agreement with the observation. We have some idea why there's a departure. The observed value is 0.22290, but we are getting something which is close to 0.25. Okay. Yes. What kind of space-time and vector bundle picture do we expect to emerge after the symmetry breaking has taken place? That is also a left-right symmetry breaking. In this theory, this symmetry breaking is also the electroweak symmetry breaking. So the claim is that there is a unification about the electroweak scale where gravity and the standard model are getting unified. So the SU2L and SU2R are claimed that they emerge together. So basically this branching, if we go back for a minute, is fundamental. So this all is claimed to happen in one go. And our understanding is that this is precipitated by a quantum to classical transition, which is responsible for the electroweak as well as the left-right symmetry breaking. So now let's recall that I mentioned this second 4D space-time when we looked at the branching of CL03. I noted that we seem to get 2 space-times out, not just one. So what could be the possible interpretation? If nothing else, it looks very pretty and harmonious. One of these 4D spacetimes is being curved by general relativity. I'll come to this in a moment. Why do we think this SU2R is going to give us GR? So 3 generations of right-handed quarks and leptons, an SU2R symmetry from which GR is to be recovered on this 4D spacetime, on which the vector bundle is giving SU3 grav cross U1 grav. The second 4D spacetime, now this is a suggestion which we need to eventually prove, that the weak force is actually the geometry of this second 4D spacetime. The weak force is not strictly an internal symmetry. Our universe seems to possess, if this theory is to be believed, a second 4D spacetime with its own light cone structure, This actually will emerge naturally from the branching of CL03. CL03, if you write it as two copies, uh, CL3 as two copies, CL2 plus CL2, each one of them will give its own space-time. That seems unavoidable. And the best guess is that the geometry of the second spacetime is given by the weak force, the three generations of left-handed quarks and leptons, and the fiber, the vector bundle is SU3 color cross U1 electromagnetic. And both these sectors are being coupled by the Higgs. And if true, then this picture looks quite nice. And why do we think SU2R would give us general relativity? We are trying to follow up on recent work by Peter Voigt, where he says that taking the Euclidean signature spacetime with its local spin 4 group of spacetime symmetries as fundamental, one can consistently gauge the SU2R factor to get a chiral spin connection formulation of general relativity. So at least in the Euclidean signature, White is arguing that SU2R gauge symmetry chiral symmetry can give us GR and the SU2L factor to get part of the standard model gauge fields. Reconstructing a Lorentz signature theory requires introducing a degree of freedom specifying the imaginary time direction, which will play the role of the Higgs field. So this question of how to go from Euclidean to Lorentzian remains there. Perhaps it's not a serious problem for us because our discussion of the emergence of gravity from SU2R will take place at the level of the split bioctonion, not at the space-time level. And the underlying level, there isn't really an issue whether it's Euclidean or Lorentzian. So if we can recover GR at the quaternionic space level and then do the squaring, we probably may be able to get a Lorentzian signature spacetime, though that remains to be done. But we are hopeful that we will be able to show that this part is general relativity. This is more challenging. It's a very, although there have been for a long time the idea that there is some connection between weak force and general relativity. The weak force is not necessarily an internal symmetry because it violates parity. And parity is a space-time symmetry. So how does the weak force know about space-time? This is one possible way. If there is a second 4D space-time. So every point in space-time in our universe actually belongs to both these space-times, which also, and one can argue that dimensions in the second space-time are microscopic. They are of the order of the range of the weak force. The universe may be much smaller in the second space-time, and it is interesting that this could serve as a EPR channel for understanding apparent quantum non-locality, because this has its own light cone. So the motion is causal, but because distances are not macroscopic, they're microscopic, Alice and Bob can communicate through this channel much more quickly. And there is also a somewhat fancy idea. Are there waves of the weak force? Just as there are gravitational waves, will we be able to talk of weak force waves or generate weak force waves? We are, with some experimentalists, we are beginning to look at this. Okay, so this I think I can go over quickly just to build up on the work of Paul Fury and others, and you can already anticipate it. How to understand the E8 cross E8 particle content in the language of Clifford algebras. So we know that one CL6 gives one generation of quarks and leptons, as Paul Fury showed us, under the unbroken standard model symmetry SU3 color cross U1 electromagnetic. Here the U1 quantum number is electric charge. We now specialize that. We here take the left-handed neutrino as the idempotent. So what we get is left-handed quarks and leptons and their right-handed antiparticles. These are triplets, anti-down quark, up quark, the positron and the left-handed neutrino are singlets, they're antiparticles. What do we do with the other Cl6? Keeping what we did with the second Cl6, we will interchange the position of the electron with the down quark. So now this is SU3 grav cross U1 grav. So this is SU3 grav cross U1 grav. The U1 quantum number is not electric charge, it's square root of mass. Same eigenvalue, 0, 1/3, 2/3, 1. But 1/3 now assigned as to the electron and 1 assigned to the down quark because it is for square root mass. So down quark is a singlet of SU. So this we can do just as for E8 cross E8. This reconfirms that. And the Clifford algebra here is CL7, which is a sum of 2 copies of CL6, one for left-handed particles, one for right-handed particles. And in principle, this can, of course, be done for each generation. So what are we saying here? How to bring in SU2 symmetry? We tensor product the Cl6 with the Cl2, which gives us the weak isospin, but as a part of the second space-time. And together, this gives us Cl8. And for the right-handed sector, a Cl2 from which we get the standard Lorentz algebra and another Cl8. And we propose to unify gravity and the standard model. Cl8 plus Cl8, which is Cl9, which can be written as Cl7 product Cl2, which is like Cl6 plus Cl6 product Cl2. So we can write in different ways to convey the meaning of as to what is going on. And this construction can be done for every one of the 3 fermion generations. And our understanding is that the triality property of SO8 imposes a triality property on Cl8, which relates the 3 representations, the vector representation and the 2 spinor representations through triality. So if I have, let's say, 2 generations left-handed quarks and leptons, with triality, I can send it to this pair CA. And if we consider, so PQR are right-handed 3 generations, ABC are left-handed 3 generations. And triality, it suggests that one copy of CL9 is enough to generate all the 3 generations. And CL9, which is because of Bott periodicity, 16 by 16 complex matrices is the rep. So that has 512 degrees of freedom. And if there is a reason why the diagonal entries should be real, then there is an interesting match with E8 cross E8 496 at the level of particle counting. So it seems to us that E8 cross E8 is one way of describing the symmetry. CL8 plus CL8 equals CL9 is another way of describing the unification. Okay, so I'm slowly inching towards the end. I hope to finish in not more than 10 minutes. Okay.
That's fine. Go ahead.
That's okay? Okay,
Please go ahead, please.
Thank you. So we have a dynamics, we have a trace dynamics, we have a Lagrangian, we have a coordinate system, the 16D split octonionic space, on which we define chiral fermions, standard model gauge bosons, a new set of gauge bosons which we relate to gravity. We see that all those results are reproduced through the Clifford algebra structure CL6 cross CL2, and then which gives a CL8, one more CL8 together. So it seems to us that everything fits together, and it interestingly yields something, at least a post-diction. What is the philosophy? Why do we think fundamental constants of the standard model can already be calculated in this framework without appealing to some high energy physics beyond the TV scale, something like guts? So why do we think this works? And the answer to that is that what we have been doing so far, here are classical systems and classical spacetime. Quantum systems live on a quantum spacetime, by which I mean the split bioctonionic space. What we have been doing so far is, so I call this quantum world versus classical world. The exact description of the standard model is at the upper level. Its current description is like this: quantum systems, but classical spacetime, R4, a bit taken care of by the Dirac operator, but not completely so. We have been missing out on the octonions. We have been working only with quaternions. The moment we include octonions, we see a unification of the vector bundle and space-time. And we may be able to recover 4D space-time along with the second space-time copy, plus standard model gauge fields, plus something new, GR, plus two other uh, so-called gravitating forces. So this level should be worked at. This level should be worked at without any change of energy scale. That's really important. When we go from quaternions to octonions, we have not changed the energy scale. So now, gravitation is the curving of Minkowski spacetime. The split bioctonionic space is the quantum analog of Minkowski spacetime. So there is a limit in which the trace dynamics variables QB, QB dot, QF, QF dot all go to identity. Let's call that the flat space limit of a quantum spacetime, which is the free limit. So let's say in GR, we add curvature and we go to higher energies by adding matter to Minkowski spacetime. We don't think of removing matter from very high energy scales and then coming to Minkowski. It's the other way around. We start from Minkowski and we start curving it by adding matter and going to higher energies. Similarly, we would like to think of introducing other forces of nature by curving or modifying the geometry of the flat split bioctonic space by adding trace dynamical variables. The limiting values of the coupling constants in the flat bioctonionic limit, these limiting values of coupling constants are determined by the bioctonic space at low energies itself. This space is non-commutative, which is non-associative. It has a very non-trivial algebraic structure, even in the flat space-time limit, unlike Minkowski. And that is why it is able to determine coupling constants per se, even at low energies. Coupling constants run from low energy to high energy, not the other way around. The standard thinking in particle physics is that there is a high energy theory, maybe at the Planck scale or at the Guts scale, which will fix the coupling constants and let them run down. And that is how the low energy fine structure constant or mass ratios will be determined. But we are disagreeing with that. It's the other way around. We determine fundamental constants in the flat limit and then let them run to higher energy. So that's the motivation. And why the exceptional Jordan algebra is important, a little bit of history. As you know, in this famous paper, Jordan introduced the Jordan product, which is the commutator of the matrix product, symmetrized and a half. And the Jordan product is interesting because Hermitian matrices form a closed algebra under the Jordan product, which is commutative, non-associative, power associative, satisfying the Jordan identity. Unlike the matrix multiplication of Hermitian matrices, which doesn't form a closed algebra. So they're looking for a so-called better formulation of quantum mechanics right in the 1930s. The Jordan algebra is equivalent to the ordinary matrix algebra of Hermitian matrices of arbitrary dimension. This is what they showed. For when the matrices are made up of reals, complex numbers, or quaternions, there is an equivalence, and hence ordinary quantum mechanics can be recovered. So the view was, why bother? We can work with Hermitian operators and standard quantum mechanics without having to bother with Jordan's formulation, except there was one case, the case of 3 by 3 Hermitian matrices with octonionic entries, which doesn't reduce to standard quantum mechanics, and the authors concluded essentially new results in contrast to the present content of quantum mechanics are only to be expected in this one exceptional case, and which is what we find now, that the EJ, the exceptional Jordan algebra J38, it seems very crucial in fixing fundamental dimensionless constants. It was forgotten, but it should not have been forgotten. That is the claim. So what is J30? 3 by 3 Hermitian matrix with octonionic entries. X1, X2, X3 are octonionic are octonions. The tildes are their conjugates. The diagonals are real numbers. The automorphism group of the exceptional Jordan algebra is the second largest exceptional group, F4. So G2, F4, E6, E7, E8. E6 and E8 we have already seen. This is our first introduction, first encounter with F4 in the present context. And the complexified EJA has the automorphism group E6. There is a, I won't have time, very clear connection between what we have been talking so far about FE6 and what we see here now. One can argue that this algebra describes 3 generations once you select the charge. If the electric charge basically be given by the diagonal entries. If it's a neutrino, Xi1, Xi2, Xi3 will all be 0. And we have octonionic representations from the Furie's procedure for all 3 generations. If it is a down quark, this will be -1/3, -1/3, -1/3, up quark 2/3, 2/3, 2/3, and electron, or suppose a positron, 1, 1, 1. And but now this is important. I can do the same thing for the right-handed fermions, where now these entries will be square root mass. 0 for the right-handed neutrino, 1/3 for the electron, because now these are mass square root masses. So electrons square root mass 1/3, 1/3, 1/3. Up quark, interestingly, remains unchanged. It is at 2/3 square root mass, and the down quark mass 1, 1, 1 square root mass. This algebra has a characteristic equation, which is a cubic, whose roots are of great interest to us. The cubic is automorphism invariant in terms of the eigenvalues, which are determined by the trace of the matrix, which is here. The 2 form, which is given like this. All of these are real. These are Hermitian matrices, so the roots are going to be real, and the determinant, which is defined here. So what we did, firstly, we argue that this describes 3 fermion generations, left-handed with the electric charge as eigenvalues, right-handed with square root mass as eigenvalues. So this is the neutrino Jordan matrix, the positron Jordan matrix. 3 generations, the positron family, the electron, the muon, and the tau lepton. The up quark family, up, charm, and top. The down quark family, down, strange, and bottom. And what do? We know these octonionic representations. We can solve the characteristic equation. These are the eigenvalues, which turn out to be very simple and, to my understanding, important numbers. They have a very simple structure. One of the roots coincides with the electric charge value. So like 0, 1/3, 2/3, 1. Two other roots are equally placed around the central root, separated in every case by the value root 3/8, except for the neutrino case, where the separation is root 3/2 minus root 3/2. This for the left-handed fermions. This first column refers to the value that LP square by L square will take. This is the magnitude of the octonion. So this I have shown. So what do the corresponding eigenmatrices mean? What is the interpretation? What is the basis in which these matrices are getting expanded? That is shown here. A, B, and C, we can argue, are matrices, 3/3 matrices, with an associated quantum number 1/3, which are basis states prior to symmetry breaking. Prior to the left-right symmetry breaking, all states have an associated quantum number 1/3. But after symmetry breaking, the left-handed fermions, a generation of left-handed fermions with a given charge gets superposed as a sum of these three states. That's the interpretation of these eigenvalues. The same we can do for the right-handed fermions with the diagonal entries as square root mass. But now a switch happens. Q gets replaced by root m. So the coefficient of A is the eigenvalue root m plus 3/8. There's a flip. And here C has an eigenvalue root m minus root 3/8. This one remains unchanged. Q just becomes root m. Those are the values shown here. The import of this representation. So what has happened in terms of eigenvalues? The down quark family and the charged lepton family will interchange places. They will flip. Up quark family remains unmoved. But the Jordan eigenvalues for the left-handed down quarks become the Jordan eigenvalues for the right-handed electron family. And the left-handed down quark, left-handed charged lepton values become eigenvalues for the right-handed down quark family. It is this flip which allowed us to derive mass ratios. Charged eigenstates are not mass eigenstates. That is very clear even from the construction. But all our measurements, including when we want to measure the mass of an elementary particle, we are only actually using electromagnetic measurements, using charge eigenstates. So what we can do, we can take a mass eigenstate from here and write it as a superposition of charge eigenstates. When that is done, the weights, the coefficients in this superposition determine mass ratio. So what is very important to remember, at the fundamental level, mass ratios are always 0, 1/3, 2/3, 1 for all the three generations. Just as electric charge ratios are 0, 1/3, 2/3, 1 for all three generations, square root mass ratios are 0, 1/3, 2/3, and 1 for all three generations. But because charge eigenstates are not mass eigenstates, and we make our mass measurements using charge eigenstates, the mass ratios appear weird, and in fact, they can be deduced from this expansion that I just showed you. This is the result. If the down quark, so this we claim are fundamental numbers which have the same status as electric charge ratios. This is the result. If the down quark is 1, square root mass ratios of charged fermions. Down quark is 1, up quark is 2/3, positron is 1/3, strange bottom. What made us very happy was that the top, even though it is very, very massive, its mass ratio, square root mass ratio to the down quark is this elementary fraction, it turns out that 2 by 3 is very close to root 3 by 8. So that gives a blow up of around 400, pushing the top quark mass high. So the claim is that's actually, everything is coming out of these simple numbers. And the agreement, which needs to be improved, is not too bad. I would say the muon to the electron square root mass ratio. This is the experimental range. Tau lepton to the electron, again slightly outside, and because when the range is higher, we are doing better. The charm to up is decent, the top to up is decent, strange to down is slightly outside, and bottom to down is okay. So, and we also have some understanding for why the mismatch is there, and we think we can try to make corrections to improve this. I think I will rush through this now because I want to leave some time for discussion. Once we know square root mass ratios, we could use that to express flavor eigenstates of quarks in terms of mass eigenstates, and use that transformation to actually work out the CKM matrix parameters in this paper. We don't know how to do the phase. The CP violating phase, we don't know right now to do. These are our results for the CKM mixing angles. This is theory, this is experiment. Again, we're sort of doing okay. We need to do better. But here at least we understand why there's a mismatch, because we are using asymptotic values of mass ratios calculated in the free limit, whereas here what should be going in is actually masses which are running with the energy and changing because of interaction. We have to work more on this to improve this. And again, let's leave this for the discussion session. Arguments similar to what I just showed you using these Jordan eigenvalues in combination with the Lagrangian yield a nice expression for the fine structure constant. But this always gets a bad name because it has been tried by various people in the past. We get a simple expression for the 1 by 137. We claim we were not doing numerology. So it has come out of the exceptional Jordan algebra. So at least for me, this is a nice expression for the fine structure constant. And some more remarks about the relation between the exceptional Jordan algebra and the very interesting octonionic projective plane OP2. There's a nice discussion in the paper by John Baez. And we are trying to understand what is the relation between elementary particles and OP2. One very interesting point is that there are no octonionic projective spaces OPN for n greater than 2. The classic Lie algebras will give us projective planes for CPN, HPN, for all n going to infinity. But because of the non-associativity of the octonions, J38, the exceptional Jordan algebra, generates OP2, but since there is nothing beyond 3 by 3 Hermitian octonionic matrices, there's nothing beyond OP2. And OP2 may be relatable to the split bioctonionic space, and that suggests to us, have we found a Lagrangian on OP2, which is fundamental? There are no higher order corrections. There is a unification happening at the electroweak scale, above which there is a scale invariant theory. The Lagrangian is scale invariant, and then it breaks into what we showed, a part which actually will be CPT invariant if you include the negative square root M branch, antimatter branch. So Turok and Lathamboyle have proposed a CPT symmetric universe in which the Big Bang produced 2 copies, our universe and a time reversed copy. In that picture, which is what seems to match with us, we have a scale invariant Lagrangian breaking into a CPT invariant Lagrangian if you include the mirror copy. And maybe the OP2, the fact that there's nothing, no projective space beyond OP2 might suggest that above the TV scale, all the way up to the Planck scale, there's just a desert. There's a scale invariant cosmic expansion, which is resetting the Planck scale from 10 to the 19 GeV to the electroweak scale, and then the observed universe emerges. This is the hard part. We're still working at it. And I think I probably leave some time for discussion. So as I said, trace quantization involved raising eigenvalues to operators. The spontaneous localization process, which will operate in this theory, because the fundamental Hamiltonian is not self-adjoint, that will send each Dirac operator back to one of its eigenvalues. And together from there, we hope to recover the observed classical fields. And this is still work in progress. I think I'll leave you with this slide. If you could kindly go through it so that there is some time for discussion. I'm so sorry I overshot. Thanks for listening to me. Thanks so much.
Thank you, Tejinder, for this impressive seminar. So, I mean, that was quite a lecture, I have to say, even if you run over time, but I think it was worthwhile. And indeed, I mean, so I think we're beginning here with some questions. Maybe David Chester would like to read out his comments or questions. David, shall I unmute you?
Yeah, sure. Can you guys hear me?
Please go ahead. Yes,
thanks for the talk, Tejinder. I appreciate it.
Thank you. Thank you.
I just had a question about the fields in your Lagrangian. So you have these variables QB and QF. Are they associated with any representations of E8 or any representations of subalgebras of E8? And if so, which representations?
I mean, it is the bosonic branching would be like SU3 cross SU2 cross U1 repeated in two copies, one for the left-hand part and one for the right-hand part. So the bosons would be in the adjoint representation. The fermion part of the Lagrangian, we are still looking at the interacting part. So I don't want to say anything until it comes up, but we are okay with the bosons.
Okay, so you're associating it with those gauge group, the adjoint representations of the SU3 cross SU2 cross U1s.
Yes.
Okay.
Yeah.
Thanks.
Yeah. Thank you.
I also have a number of questions. In the meantime, if in the meantime anyone has anything to say, please put your hands up. Tejinder, what is it that induces left-right symmetry breaking? This came towards the end of your talk.
Yeah, my understanding is that this is happening. So because of a quantum to classical transition in the early universe. What is my picture is that a 4 acceleration imprinted on the 3 acceleration of the expanding universe is playing an important part. So I started with the assumption that the universe has 10 to the power 80 observed particles. Our universe is 10 to the 80 particles. And a scale invariant expansion, which I don't like to call inflation because that brings some other ideas, but it's a scale invariant cosmic expansion, which ends with the quantum to classical transition at the following criterion, that I can associate a black hole with 10 to the 80 particles. I can think of a black hole which has the same number of particles and as the observed universe, and ask what is the surface gravity of such a black hole. That turns out is known to be of the order as the Mond acceleration, 10 to the minus 8 centimeters per second square. So this scale invariant expansion lowers the acceleration of the expanding universe when that becomes equal to the surface gravity of a black hole with the same mass as the observed universe. Symmetry breaking takes place because now structures can form. Until the expanding acceleration is higher than the critical black hole acceleration, structures cannot form. That's the criterion. Formation of structures induces classicality, and that breaks left-right symmetry as if two 4D space-times, what I call the second space-time and the first space-time. So that is also a left-right symmetry breaking.
I see. I mean, it sounds plausible, to me at least. I think we have
Anthony has a question.
2 or more people have put up their hands. So we have, I think, B. Hens in the first place. And we have Anthony as well. Anthony, please go ahead.
Hello. Thanks so much for the lecture. Can you hear me okay?
Yeah, thank you. Please go ahead.
Right. So what I'm not clear about at the moment is for the Jordan exceptional algebra, how you know how to assign the various states to that. Because I can't at the moment quite see the connection with the earlier part of your talk.
Okay.
How you know what entries to put in there, if I can put it that way.
Very nicely put, very nicely put. So you are asking, how do I know that the exceptional Jordan algebra describes 3 fermion generations? And the diagonal entries are the electric charges, and the off diagonals are the octonionic construction, say a la Cold Fury. That's the question, no?
Yes.
Yeah, okay. So I will try to share my slides once again, because the slide on the octonionic projective plane is what I missed, and I need to. So let me get there. I think I can do that. Okay. So this is so the most naive answer would be that we just assumed that J38 represents 3 fermion generation, but probably we can do a little better. What I learned from John Baez's review articles is that if we look at the projections of J30, elements P, so that P square is P, the projections of J30 up to automorphisms, they take only one out of these following 4 forms. These are 3 by 3 diagonal matrices. One which are the diagonal entry 0, trace 0. Another which is trace 1, trace 2, trace 3. At least heuristically, this strongly suggests to me that this is the neutrino. This is the electron, if I'm looking at electric charge. No, this is the down quark, if I'm looking at electric charge, or anti-down quark. This is the up quark, because the trace is 2, and this is the electron. So why only, let's say, these 4 possible projections? This suggests strongly that these represent the 4 quarks and leptons after suppressing color. And with this, I can associate a charge 0, charge 1/3, charge 2/3, and charge 1. And similarly for square root. Well, this was my motivation for believing that J30 represents elementary particles of the standard model. And then because the automorphism, up to automorphisms, I could reduce to this form, we just went ahead and assumed. So strictly speaking, you could say that I have made an assumption. I don't know how to relate Clifford algebra CL6 states to J38 entries. So if you are looking for a direct proof, I think I'm missing that. but I have this, let's say, arguments in favor of why that might be correct. Does this help in any way? I like your criticism.
Yeah, it does help. I can see the motivation via triality. I suppose I'm thinking one could do that and make those assignments without the earlier part of your work. Is that fair?
Right away work with J38 by appealing to triality. That's what you're saying?
Yes, yes.
Yeah, so my question then would be, how would I construct the spinors for these elementary particles unless I did it in Cole's way using CL6? That's where, I mean, like we talked in the Israel conference, I'm very hopeful that this can be done using your geometric algebra way. If you have states, geometric algebra states for one generation, and if we could use a SU3 gen by appealing to E8 cross E8, if you could do that to get geometric algebra states for all 3 generations, and if we could then somehow argue that that is related to J38, I think we would have done it without going to the Clifford algebra. What is, I think I asked you there also, do we understand how J38 is related to geometric algebra?
No, that's something I'm working on right at the moment, indeed.
Oh, that'll be great. That'll be great. I think it'll be this, for example, this root 3/8, which is occurring in these Jordan eigenvalues. It is too simple a quantity for having to need these characteristic cubic equation, because that cubic equation gives numbers like some 72 over 512 and this and that. I think this must be this root 3/8 is probably some angle, but I'm not able to figure out how to go about it. And I think there will be a simple answer. So if you take the geometric algebra states for left-handed fermions, and then make geometric algebra states for right-handed fermions, and find out how to express one in terms of the other, then I think you will get these Jordan eigenvalues. That's my guess. And it would be great if you have it, then we'll have these fundamental constants coming out of there.
Okay, thanks.
Thank you. Thank you for asking.
Okay, I think we have a few more questions. Let me take them in order. So we have something here in the chat from B. Hens. Will you read out your question, or shall I do it for you?
I can do it. Thank you.
Go ahead, please.
So, my question is related to the gravitational force in your model. You use spin 1 particle, so you get the vector gravity. Is this correct? So, and for spin 1 particle, maybe this is wrong. It could be totally wrong.
No,
but normally
it's the right question. It's a good question. Yes.
So for spin 1 particle exchange, I would expect that like charges, in the case of gravity, that would mean that masses would repel each other.
Yes, yes. So my proposal is, as you know, there are 2 signs of square root mass here, plus root m, minus root m. Plus root m is for, one sign is for matter, the other sign is for antimatter. Matter and matter are attractive. Antimatter and antimatter are attractive, but matter-antimatter interaction is repulsive. So the suggestion, which can be, there's some argument in favor of this, in the very early universe, at the time of this left-right symmetry breaking, matter and antimatter universe is separated, leaving only a small fraction of antimatter in our universe. So there is an antimatter universe in the Turok-Latham-Boyle sense. So we have, does that help?
Yes, it does. Thank you.
Yeah, so a prediction is that an electron and a positron should repel according to this SU2R interaction. If we could ever check that, it would confirm or disprove this proposal.
Okay, so then, okay, thank you.
Thank you.
Vesel put up his hand a while ago. Please go ahead.
Thank you. I again want to express my gratefulness for organizing these sessions and giving wonderful talk. It became very clear to me now. I understand how the Jordan algebra is related to the quaternions and how this comes to the classification of the elementary particles. Now,
great.
I am really grateful. It was a wonderful talk, helped me a lot to understand. But I was wondering, a few times you mentioned the scale invariance and Mont, and how this are coming in your kind of approach.
Thanks for asking. So this Lagrangian, if you remember, LP squared by L squared, Q1 dot, Q2 dot, this is scale invariant because symmetry has not yet broken. When there is symmetry breaking of QB dot plus alpha by L QB, one part has a scale, the other part doesn't have a scale. So prior to symmetry breaking, when the LP square by L square is just sitting outside, that's a scale invariant theory because it won't affect my equations of motion because it's just overall scale out. But once I separate between gravity and the Young-Mills part, one of them is having a scale in it. So the gravity part will now obey the equivalence principle, but the Young-Mills part will not. And basically that is the breaking of scale invariance. Mond is supposed to be U1 grav. There are two U1s, the U1 standard model, hypercharge and then electromagnetic, and there's a U1 grav. There is something very interesting going on. You know, in Mond, as you know, the force is proportional, the acceleration is proportional now to square root of mass, not mass. The acceleration is known as root m by r. Newtonian gravitation is m by r square. Mond acceleration is root m by r. And our U1 grav is very naturally proportional to root m. This I found very interesting. I did not have to invent it. The U1 charge, U1 grav charge is square root of mass. So I could relate it to Mond, at least in the non-relativistic limit. Relativistic Mond we are looking at. So the U1 grav very strongly shows indicators of being related to Mond. What I don't know is SU3 grav. I don't know what SU3 grav is doing. We have to understand that still.
Oh, okay. Yes, that's very helpful. If you don't mind, I will share a link here to a paper on of Professor Maida. That's about Monte's version of the scale invariant vacuum theory.
This is exactly Maida, is it?
Yeah.
Okay. A peculiar is a scale. Yeah, okay, I should see this. I'll get in touch with you. And if you could kindly email me these papers, and I will try to take it from the chat. Both are Maida's papers, is it?
Yes.
Okay, I can find them. Thanks a lot. This looks very interesting.
Thank you.
Thank you. There's some other question.
Okay, we have a comment here from Hillary. Hillary, would you like to read it out for us, or shall I do it for you?
It was just a little point picking up on the suggestion about matter and antimatter maybe repelling each other. So just picking up on that, and shouldn't that produce visible energy shifts? But they might be too small to detect. So that's just me thinking out loud. Maybe it would change the energy levels of plutonium.
If it is gravity, I am apprehensive it will be very, very tiny.
Right. So then I thought a bit more and thought, well, maybe neutrons versus antineutrons.
Right. Yeah, I think this needs to be looked at. Can we detect the vector repulsion part of SU2R in some way? This needs to be looked at, yes.
We're getting background noise from somewhere.
Not mine.
No, it's not yours. It's
yeah. Jose, I think David has an interesting comment. We lost Jose.
No, I'm here.
Yeah, so yeah, please go ahead.
Yeah, well,
David has a comment about OP2.
who's next?
Yeah, I mean, if you
Go
just
ahead.
took the poly matrix sigma z, that gives you that you can use that for a split complex imaginary unit, and then you could embed that in a 3x3 matrix.
OP2 can be found. Do you understand the relation between OP2 and the CL6 fermion classification? The way John Baez puts it, I think different. So he says that the lines of the OP2 are trace 2 projections, and the points are trace 1 projections, which would make them essentially, the down quark and the up quark. So I would like to understand what is the physics going on here. If you try to understand the lines and points of OP2 in terms of particles, I mean, that looks quite nice, actually.
Yeah, I mean, there's often multiple ways to apply physics to the mathematics. So if you just start with mathematical definitions, there could be multiple ways. But yeah, I mean, I just put out a paper with some collaborators of uplifting Colfuri's stuff to projective lines, and you might guess where we might go next.
I will see that. I'll see. So you already have work on that, yes.
Yeah, so I think Colfuri's work can be uplifted to generalized projective geometries.
Great. Excellent. That would be that's very interesting. Maybe we learn something new from there, or it's just a translation of Furi's result in projective language.
Well, so far we've put out the projective line work, which just simply demonstrated that all of Cole's results can be uplifted to the line, so that within itself didn't have new physics. But yeah, we're currently.
It's a good insight. It is telling us various ways in which the octonionic mathematics is related to the standard model. And what I was looking at was, can one from the projective plane get chiral fermions? I mean, can I talk of left-handed and right-handed fermions separately, somehow using OP2? I have not been able to see that yet.
Yeah, I put out a paper in 2020, and then it got published in 2023 that essentially did that. And then in my talk in September, I can mention how the when you uplift Colfuri's work to projective planes, and you compare that with E8, and you look at the Freudenthal-Titz construction, you can actually see that there's a secret unexplored Freudenthal-Titz construction that's the most exceptional, that kind of unifies E8 and Colfuri's approach. But I personally don't like putting physics there, but it's just a mathematical statement. So I'll elaborate on that more, but yeah.
But you might be able to get gravity in also somehow, and that would be nice.
Yeah.
Thank you. Thank you.
If I may make one more question, I like the, shall I say, duality between the weak force and general relativity. Does that in any way link up with current ideas in string theory about the gauge gravity?
That's a very good point.
I know your construction is independent of string theory, but of course what you're proposing here is a duality in a sense.
Right. So if you look at QB dot and QB, at least naively it seems that QB dot has one more dimension than QB, because it's a velocity, it has brought in a time derivative. So if QB dots are gravitational degrees of freedom, they might be in a sense living in the bulk, and the QBs are to be thought of as being on the boundary. That is the gauge gravity duality in the anticipated way. The gauge fields are living on the boundary and gravity is in the bulk. That is one that that might, and there may be some hints of ADS-CFT in this. We can look at that. So since you mentioned string theory, my picture right now is what we are doing in this picture is, or string theory is this proposal without the octonionic space. They define strings on a Minkowski background and they start to build perturbation theory, but it's difficult to recover the non-perturbative theory from. The non-perturbative version is simply writing the string on a split bioctonionic space. Already your manifold is non-commutative. So what I have is a two-brain on a non-commutative split bioctonionic space. My guess is if they do string theory right from the beginning on an octonionic coordinate system, bioctonionic coordinate system, everything should start working. And E8 cross E8, this is important. Why did they also have E8 cross E8? It was one of the two, proposed heterotic string theories, the other being SO32. So there clearly has to be a commonality. Why they picked E8 cross E8, why we also do seem to do well with E8 cross E8, there must be a commonality, and the commonality is we have octonions. They did not pay, in my opinion, importance to octonions the way they should have. And if they do, I think it will become the same theory.
Well, that's a bold statement to make. I'm not at all sure string theorists would adhere to that. But anyway, I mean, I do agree that there's a strong hint of some common ground.
They need some new input to bring them out of the current, block of not being able to reproduce the standard model. Compactification, in my opinion, doesn't work. I think the landscape and trying to find the standard model in that, in my opinion, is not the right way to do it. No compactification. We didn't compactify. We didn't have to because we are in some sense working with brane worlds. The extra dimensions are not Planck length. They are of the order of the range of the strong and the weak force, which sounds okay. And so string theory with some new inputs can be made to work. And I'm making a statement that it will become the present octonionic theory. And they may like it or not like it, but that's okay.
Well, we'll have to wait and see. I think David has a comment on that. David.
Yeah,
please.
I mean, there's already plenty of literature showing how the octonions are related to supersymmetry and D equals 9+1. And Michael Duff has published many works showing how the division algebras classify all of the supergravity theories, and supergravity is the low energy limit of string theory. So, maybe
you understand it better, David. What is the difference between, say, what I described and the string E8 cross E8?
I mean, I guess I don't fully understand how your Lagrangian connects to E8 cross E8. First of all, I mean, I guess they explore different branchings.
Yeah, I think so. One important thing is, to my understanding, to introduce this square root mass and to accept that gravity is to be generated from a SU to R symmetry, which is something they may not be ready for. And that those might be the standard model part would be similar, but how to deal with gravity in E8 cross E8 might be an important difference to my understanding.
Yeah, you have different gravitational views as well.
Right.
I think B Hans has a comment to make. Please go ahead.
I'm just wondering whether the octonion may be to string theory what the complex numbers are for quantum mechanics.
Absolutely, that's very nicely put. I would agree with that. Yeah, so also, like, why does it work in 9+1 dimensions? Because SL2O is the double cover of SO19. There clearly is a connection with the octonions, and I think they should have seen it by now.
I have an additional question, but maybe to the whole audience and especially to David, he needs to be an expert. Have people in string theory ever looked at general Hermitian matrices over the octonions beyond the exceptional Jordan algebra?
There were papers on the exceptional Jordan algebra and string.
Yeah, and I'm wondering whether they go beyond this. So there are also, well, there are more than 3 times 3 Hermitian matrices over the octonions. There are, for example, 4 times 4, you name it.
But they are not Jordan algebras, are they?
No, they are not. They're most definitely not Jordan algebras. This was a huge disappointment originally for Jordan and for Neumann and Wigner when they found out that these algebras are not Jordan algebras, but I'm just curious whether anybody have in theoretical physics have looked at the more general matrix algebras over the octonions.
No, I don't know.
Nobody seems to know. Okay.
Yeah, I mean, most people stop at 3 by 3 because the statement is that you can't get quantum observables if you go beyond the exceptional Jordan algebra. So that's the typical obstruction. So it's almost perceived as being, if you want to do quantum theory, then you shouldn't study 4 by 4 octonion. But there is work by Tapan who talks about an octonionic formulation of M theory as well. And he discusses I think what he's actually doing is using 2 different 2-component octonionic spinners. So then he ends up getting 4 by 4 structures, but you should really almost think of it as like a pairing of 2 2 by 2 pieces. And so that's an example, Topan.
Okay.
Toppan.
Thank you very much. Okay, then I'm done with my questions. So.
Thank you. Thank you. Any more questions or comments? If not, may I come back just very briefly to your comment about the coupling constants in particle physics running from high energy to down to low energy. And you said you're actually reverting the sense of that flow, that renormalization group flow. Will you please comment on that?
Okay, let's go back. What I was saying was, if you look at the octonion as a coordinate system, O equals 8 directions. And then I start adding these Adler's dynamical matrices as coefficients of these different octonionic directions. That is like adding matter and gauge fields. Before I added them, suppose all the matrices are identity, I have what I call the non-commutative analog of flat Minkowski spacetime. No matter and gauge degrees of freedom, but the flat limit of quantum systems is not Minkowski spacetime. It is the octonionic space or the bioctonionic space. In this space, I have left-handed fermions with their electric charge eigenstates, right-handed fermions with their square root mass eigenstates. These are not the same, but they are relatable. They are expandable one in terms of the other. And this non-trivial property is what gives rise to the limiting values of coupling constants. The flat space-time octonionic limit is non-trivial, unlike Minkowski flat. There's no information. You cannot conclude anything from there, but that's not so for the octonions because of the non-commutativity and non-associativity. So the limiting values of coupling constants are getting determined at this low energy flat limit of the octonion. And then I add matter and gauge fields like in gravity. In gravity, I go to higher energies by adding matter. Here also, I will go to higher energies by adding gauge fields and fermions to the octonionic space. But before I go up, I'm already constrained from down. My fine structure constant is 1 by 137, no matter what. and then it flows. This has met with great resistance. I talked to particle physicists, they just don't believe this, but I think it's also the mindset.
I see. David, I think you have some more comments to make. Please go ahead.
I was just replying to, yeah, but I mean, you could use octonions for classical theory. So I mean, once again, it depends on how you apply the mathematics. I don't think there's anything inherently I mean, also there's nothing inherently special about quantum mechanics being complex, but that's just a reply to a comment, nothing major.
I agree. All I'm saying is that R4 versus octonions as manifolds has significant differences. That's all I'm trying to say.
Yeah, for sure. Yeah, my comments were really just replying to B. Hen's comment.
Okay,
So,
yeah. Do these comments get preserved in the recording, Jose?
I think in principle, we're recording everything, including the chat.
The written comments also get preserved.
I think so, yes, I would say so.
They are important. They are a part of our record, yeah.
I would think everything gets recorded. So everything you write into the chat or everything you say,
Okay.
I would guess, yeah.
Mm-hmm.
Any more questions or comments?
I'm just saying it says it's being recorded.
Okay.
And I think I found a link to Mia Hughes's thesis. I put it in the chat.
Yeah. Thank you. Yeah, I know Mia's work. So that was in what context?
Well, she discussed how octonions are used in supergravity. So.
Oh yes.
Yeah, somebody asked for a link to her thesis, so I found it.
Yeah. Thank you. Yeah.
Thank you. I was the person asking for the link, and thank you very much. And I agree with David. So he commented on my comment concerning complex numbers and octonions, and I see what he's about what he has to say, and I understand and accept it. So to speak. So, and thank you very much to Hillary for providing the link.
Okay. Would anyone want to say something, comment on something, ask a question?
If I may be allowed, Jose, so I'll ask you, what is your verdict? Is it right? Is it wrong? Is it worth pursuing? But I mean, I would like to know what you think.
I'm sorry, I didn't hear your question. Can you?
This unification proposal,
yeah.
Do you see some difficulties which might just bring it down? Or is it worth pursuing to fill in?
Oh, I see. Oh, so you want my opinion on the proposal as a whole?
Yes.
I think it's very consistent, to the best of my understanding. Of course, one has to make a prediction, because otherwise we run the risk of being taken for string theorists.
Yes. Not just post-dict, predict.
Yeah, well, post-dicting is also important, of course, but predicting is even more important.
Yeah.
And
so the closest we have come is actually not particle physics, but these super quantum non-local correlations. That's at least a clean signature, but it's a number. What by prediction, I think you mean can come up with a number which can be compared with the quantum field theory prediction through an experiment.
Exactly.
I agree. We are, so I forgot to mention, we are starting to study interactions. Interactions should be described as matrix valued collisions in phase space, from which we should build Feynman diagrams and perturbation theory. Then we might be able to do, but that's for the future. You're right. There's no prediction. There's no prediction yet.
Yeah, well, what I find very impressive is, of course, the long list of mass ratios that you have and coupling constants and the Weinberg angle and the CKM matrix and all that. To the best of my knowledge, there appears to be no rationale within standard physics, within QFT, standard QFT and string theory that would account for these measured values.
I think the reason probably can be said to be that we didn't work with the octonion algebra. All the non-trivialities because of the octonions and the exceptional Jordan algebra. It's like, when Jordan, Wigner, and von Neumann said, this is one case which might give new physics, which is not there in the standard formalism. This is there in the paper, in the conclusion, but we forgot it, right? It's like we forgot, since the rest of the Jordan formalism is same as quantum theory, we threw the baby away with the bath. And maybe that's the reason why this will give new information.
Yeah, but I think it's also written in the paper that the example they have found. So Jordan, Neumann, and Wigner stated also in the paper that the example they found is too small or too narrow to be used as an extension of quantum theory. And I think this message carried along, and so people only looked at the mathematical side of the exceptional Jordan algebra for a long time because they thought the verdict of the founders of Jordan theory was this is simply we don't have enough examples of exceptional Jordan algebra. We have only one example, and what are you going to do with one example? I think this was the reason why people.
I think the picture is that if it is finite dimensional, but by taking many copies of the algebra, infinitely many, say, one per particle, you can generate space-time. So at that time, the worry was, if you use it, how do you get a continuum? How do you get infinite?
Yeah, exactly. How do you get more? Well,
my answer to that is you do this, you take infinite copies of this algebra.
Okay.
One per particle, so to say.
Okay, and I guess I understand why they didn't try this. They noticed that if you take a copy of the exceptional Jordan algebra and build a tensor product within another Jordan algebra, the tensor product is no longer a Jordan algebra. So you cannot use the exceptional Jordan algebra to form tensor products. So to build multiple particle states in the normal quantum field theory sense, if you take.
I agree, but what I was suggesting was that we need these multiple copies really only in the classical limit. One fellow in the classical limit gives me one space-time point, the other one gives me another space-time point.
Okay.
And at least at that level, I can form a continuum.
So this is important that I understand what you're doing. So how do you mathematically form the copies? So how do you copy the Jordan algebra? What are you going to
okay, like, this Lagrangian, this space-time matter atom Lagrangian, I just sum them up. One action.
Okay. Then everything is fine.
Yeah, I sum them up. I don't think I make a tensor product.
Then everything is fine.
That would be too difficult, I think.
Yeah, and you would lose the Jordan algebra stock here, but
yes,
I just wanted to give the historical background why they didn't do this. They thought if you use
at that time the standard model was not known the way we know it now. There were
of course, it was in the 1930s. Yes, but it is.
No quarks. Even I think very little was known, but now I think especially subsequent to Paul Furey's work, building on earlier work, we understand how to write these states. And then, when I saw Cole's work for deriving charge quantization, I was very puzzled. Why not mass quantization? How is it that you can do charge and you don't do mass? So that is how I realized that if you would introduce a new quantum number and you work with the exceptional Jordan algebra, you can get to mass quantization. That was basically a guess. And this nice cubic equation is worked out very nicely by Dre and Manogue, in the early 2000s, is there in the paper. And then it's begging to be used.
It's begging, so it's screaming into your face, so to speak. Okay, that's an interesting comment by David, which is also important to understand.
Yeah, please, David, please go ahead.
Well, yeah, as we were mentioning, yeah, it took time to realize the significance of division algebras alone in the relationship to the standard model. And also even just mathematically, it took time to understand how tensor products of division algebras with Jordan algebras relate to exceptional Lie algebras. So
yes.
yeah,
I think at least I'm very grateful for John Baez's review, which is meant for lesser mortals who can understand through his paper some mathematics. So that really helped. It's a very comprehensive review which covers most of the topics that a physicist would need.
and it's also just curious how bosonic M theory is in 26+1 dimensions.
Oh, that's J30, yes.
And why is it 26+1? Shouldn't it be 26 alone? Just
well, bosonic string theory is in 25+1 dimensions, and superstring theory is in 9+1. So then M theory adds a spatial dimension to get 10+1, and then you get.
This is known, the connection between J30 and bosonic M theory. They discovered this.
I mean, my collaborator gave a talk mentioning that this connection could be explored.
So do you know if string theorists are getting interested in the octonions? It should be obvious by now, given what's happening in the octonion community, that
Michael Duff.
Okay.
Yeah, some people know. I mean, Paul Townsend.
So what I heard from one string theorist is if they move away from compactification and more look at brain world scenarios, which is closer to what we are doing, then there will be progress. What are we trying to, in my opinion, what are we trying to get from string theory is the original hope of a unified, what they call a TOE. Why did they get stuck? I think they can come out now, taking the work that's happening in the octonion community.
Yeah, I mean, Townsend essentially discovered aspects of M theory before Witten, and then he tried to pitch that everything should be called membrane theory, and the string theorist got mad at him and said, "Oh, do you not like strings?" And he said, "No, I mean, a string is just a one brain."
Absolutely.
And now everything's all about membranes, but they still call it string theory. So
I didn't mention a quote by Townsend around 2016. He again has a paper on Jordan quantum mechanics, and he does make a note that J38 looks very important, but we don't know yet what applications it might have in particle physics. This is 2016. So I think after that, Todorov, Dubois-Ouellet, Tavian Ray, and many people are, I think. So I hope the string theorists also look at it, if they want to come out of where they are stuck.
yeah, I think there's a path forward. I think the whole field can be course corrected.
Yes, that's a good word, course correction, yes.
Sorry.
Concerning string theories and ways to get around the compactification problem, there are a few string theorists who now view the extra dimensions as truly quantum, so who give the extra dimensions not a point set structure, but some kind of operator algebra or even non-associative algebra to describe the extra dimensions. It's a little bit, but only a little bit, like Alan Kant did it. So he used the classical spacetime and then multiplied it with a quantum spacetime with a non-commutative geometry, and they are using something similar. They replaced the extra dimensions by non-commutative and non-associative structures. And there was a paper a few years ago from the string theory group in Munich. They used the octonions to describe a quantum space-time. So they have also.
But this is done only for the extra dimensions or for the?
No, the Munich paper it was from Immanuel Malek. They used the octonions to describe space-time, so to quantize. Well, it is still quantized if you go beyond associativity. So let's say, yeah, they use the non-commutative and non-associative space-time, not extra dimensions, but also to describe space and time. So
yeah, But I think something like trace dynamics may also be important, unless one can develop quantum field theory over octonionic spaces. I don't know whether that maybe that can be done, because the dynamics also has to be taken care of side by side.
That's a good question. So there was once in the 1970s until the 1990s, there was an Estonian group in Estonia. They worked on also on the octonions, and they tried to use also develop a dynamics using the octonions. There was a, yeah, I forgot the title of the paper. There was a survey paper in 1998 where they looked at this. Maybe I can try to find this and send this around to everybody. But yeah, there have been attempts to also use the to describe dynamics using the octonions and using something we learned about derivations and non-associative algebra to also get dynamics in the sense. Yes,
Yeah,
it has been tried at least. So.
yeah. So my surmise would be that we need to go to a pre-quantum theory also. That is also important for recovering classicality. And at least trace dynamics gives some hope for how to do it. Also, in my opinion, one would have to give up on things like Everett interpretation of quantum mechanics, because we need collapse of the wave function.
This would somehow fulfill one of Jordan's older dreams. So in the 1960s, he came back to generalizing quantum theory and also wrote about his attempts with Jordan algebras and the exceptional Jordan algebras. This time not to describe nuclear physics, but he tried to solve the measurement problem. He was one of the first people to call it the measurement problem in a paper from 1949 on the process of measurement in quantum mechanics. And he thought this means that quantum theory is not complete because we don't have the transition to classical and especially statistical thermodynamics. So you always.
I think I know this work from Jordan. Yes.
Sorry.
How the Born probability rule is treated in the octonionic quantum
Yeah,
mechanics.
this was also Jordan, also in 1949. So he was quite active.
I think you sent me these details. I remember. Yeah, thank you. Yeah.
Just wanted to give the reason why he was looking at this. So in 1949, he was also thinking about the measurement problem, and then he came back to the octonions and tried to generalize the Born rule, so to get a generalized quantum theory to have not the problem with the measurement. So I think I have not sent you the paper on the measurement problem. Maybe I can send this also.
Okay. Yeah. I think yeah. Thank you. Yeah, David, I agree with you about this CDT. Yes, there was a paper from the Scandinavian group. I forget who was this. Who's Ambjorn. Yes. I remember that paper. Yes. Division algebras and CDT, and how that goes towards string theory. Yes, I remember. Maybe in a few years, people outside this community will also start looking at octonions and division algebras, maybe. Yeah.
Okay. We've been discussing physics for the better part of 3 hours by now.
Yeah, I think call it a day now.
Ladies and gentlemen, shall we call it a day?
Thanks, Jose, for chairing and hosting and for a very kind introduction. Yes, thank you very much.
My pleasure. My pleasure. So a very big thanks to you for your talk. And we'll meet again in 2 weeks' time, right?
Yeah, the next talk should be very interesting. Ashutosh Kotwal, particle physics, what we know and what we do not know. I'm looking forward to that.
Me too.
Yeah.
Okay, see you guys.
Bye-bye. I'll log out.
Bye, and thank you for the nice talk.